All right, so this is going to be mostly a review day on resonance. So we've got the in-class activity. You can work on your problem of the day. I did want to bring up a couple of things, though. Number one is the best way to get good at doing resonance is doing as many practice problems as possible. So I really encourage you to open up your textbook, do all of the resonance problems if you can. The back page of the in-class activity is a particularly challenging one. I think I pulled it from the textbook. It will probably take a few pages of paper to figure out, but if you can do that challenge problem, you've mastered resonance, and you should be proud of yourself. I'll post the key to the in-class activity and the pod in OneNote so you can check your work. If you have questions, I'll be around tomorrow. I know a lot of people have questions on lab and resonance, so just shoot me an email. You can schedule a time or come to my normal office hours. All right, with resonance, there are a handful of patterns that you'll see over and over and over again, so I did want to briefly show these to you. The first one is lone pair sigma pi, right? So anytime you see a lone pair attached to a sigma bond and an adjacent pi bond, there's always going to be a resonance structure. So let's try to do one for this. For example, you could take this negative charge, move it right there. That violates the octet on the carbon, but we can fix that and we can pull the electron up to oxygen, right? So that's one option. It's pretty common. And in this example, we actually have degenerate resonance structures, right? Because they're equal contributors. One's not more important than the other. All right? The second pattern that often shows up, I call a cation sigma pi. So you've got a cation on one atom attached to a sigma bond, and then there's a pi bond next door. And I've got an example of that. We saw a few of those already, especially with the allyl cation. The next one is a non-carbon-carbon pi bond. You can break those. So in this example, we have a carbonyl where we take the pi bond, dump electrons to oxygen, and it gives you a carbocation. These are typically pretty minor contributors, and why is that? Why is this one on the right a minor contributor? Charges and octets. Octets are the first thing we look at, so this would be a pretty minor contributor. You can draw this. Why don't we do normal carbon-carbon bonds as resonance structures? Meaning, let's say I've got this molecule. Why don't I show a resonance structure that looks like this? Anybody remember why? Yeah. Yeah, exactly. Avoid drawing resonance structures where you have carbon positive and carbon negative. So this one we have carbon positive right next to a carbon negative. That's just not really worth drawing. So don't include those. But the non-carbon carbon pi bonds can be broken because then you don't have both a carbon positive and a carbon negative. All right. The last one is aromatic ring systems, and these are kind of funky, right? So if you think about benzene, you can actually rotate those double bonds through resonance. And like I said a few lecture periods ago, some people will even show benzene with a dash bond as a circle on the inside to show that delocalization, or even a solid circle on the inside. I know what those represent. However, when you do resonance structures, avoid the circles and actually show all your pi bonds. That way it will help you with the arrow pushing. Does that make sense? All right, so occasionally with these in-class activities, we'll have them in class, and I'll ask you to try to get together with a group of like 3 people and then work on them together. It won't be turned in. It's just meant to be good practice. All right? Yep.
The last one, the aromatic rings, I thought you could only move the pi bonds to adjacent atoms.
Yeah, so there's 2 options, right? Anytime you're moving a lone pair or a pi bond, you can move it to an adjacent atom or an adjacent bond, but not further than that. So in this aromatic ring system, we are moving a pi bond from one position to a new bond position, but we're not violating the octet rule, and we're not jumping an atom, so it's perfectly okay. Yeah. Any other questions? All right, good luck on the in-class activity. I'll float around, so if you have questions, you can always raise your hand and ask me.